Hello. Today we're going to start chapter 8 on rational numbers. I'm pretty excited. Let's jump right in. Okay, so rational numbers. So rational numbers is any real number that you could write as a ratio between any two integers, p and q, such that, of course, the denominator cannot be 0. So that's that's our working definition for rational numbers. When we say something is irrational, it means any real number that's not a rational number. So let's work with it. So the main benefit that we get from going from integers to rational numbers is that now we have a field. So we can divide by any rational number and get a rational number. But one complexity that we get is that it's the way we write rational numbers as ratio of two different integers is not very unique. So if you have two different rational numbers, a divided by b or c divided by d, sometimes they could be different numbers that's represented. A, b, c, and d could be different, but representing the exact same rational number. That's because we could reduce fractions to get the same number, right? So you have to check if something is same. One way to do this is just kind of cross multiply between a d and b c and show that if a times d is equal to b times c, then you have the same rational number. So that's one new complexity that we have to work with. So rational numbers is really nice because it shares some of the characteristics with integers and some other characteristics with real numbers. And it kind of seams them together, right? So one awesome thing about rational numbers is that it's countable. So there's infinitely many rational numbers, but you could list them. It has the same size, cardinality size, as natural numbers. So that's nice. And a lot of the cool theorems about integers extend to rational numbers as well. So in particular, the one I have in mind is the fundamental theorem of arithmetic, where any integer could be, there's a unique prime factorization of that. You could do the same thing with rational numbers if you change the theorem statement just a little bit. We'll get to that in a second. It is a field, so you could add, multiply, divide, you could square. You'll stay in the rational field. That's something new, so it's more convenient. And one more feature that we'll get to next time is that it's dense. What I mean by dense is that it's kind of absolutely everywhere. It's kind of like sand, it gets in everything. More formal statement would be like, if you take any distinct real numbers, then you could always find a rational number in between those two. So it's, no matter where you zoom in, there's many rational numbers that you can work with. All right, so let's first restate the fundamental theorem of arithmetic in a version that works for rational numbers as well. So one way to factorize a rational number, x, is to rewrite it this way. So it's product, so it could be negative, right? So plus or minus, so that's there. And for each prime number, the multiplicity ei could be negative as well. So if you're thinking of P and Q in the reduced form, so like they don't share any common factors, then the factorization of the numerator p will have positive multiplicities, and the factorization of the denominator q will have negative multiplicities, because when you divide by something, you have a negative power, right? So in that way, you have this factorization of rational numbers, which is kind of nice. So you inherit that from integers. Okay. So in this video, I think I want to prove one more theorem, which is about a way to parameterize a unit circle. So the most famous way that you've seen to parameterize a circle is using doing this. So you take any theta and you could write the points cosine theta, sine theta, to look at points on the unit circle. So that's one way to do it. But there's a different way to write down points on the unit circle using only one variable. So maybe not theta, but I'll use t this time. That's convenient in some cases. Let's look at it. So as long as you're not looking at the x equals -1, so the leftmost point on the unit circle, you could be on the circle if and only if there's a real number t, such that you could write the x and y in this way. So it's some kind of a rational expression using t. Furthermore, xy has rational coordinates. So when I say rational coordinates, I mean both the x and y are rational numbers, if and only if t itself is rational. So you could kind of identify points on the real number with rational coordinate points on a circle. So that's kind of nice. Okay, let's see how you might prove something like this. Okay, so let's go one direction. So I want to write down that these types of points are the same thing as points that satisfy this equation, right? So I have to go both direction because this is a if and only if type of theorem. So I think I want to go this direction first. So if it's in this form, then it's on a circle. And then after I prove that, I'll go, if it's on the circle, then it could be written in this form. So that's how I'm going to prove it. So the first thing to notice is that this expression 1 minus t squared divided by 1 plus t squared, this thing is never equal to -1. Remember that part of this parametrization is that it's all of the circle except for the leftmost point. One way to see that this thing is never equal to -1 is to see that the numerator is almost always smaller than the denominator. What I mean by that is 1 minus t squared. So t squared is non-negative. So if it's positive, it's going to cancel out a bit with 1. But in the denominator, it's added. So it's a little bit bigger in magnitude than the numerator. It could be 0 exactly. If t was equal to 0, then it's 1 divided by 1, but that's when it's equal to +1. So if you pick any other t and plug it in there, you're gonna get something in magnitude smaller than 1. So it can't be -1. Okay, so it's not on the left-hand point, but anyways, if it's in this form, this fractional form, let's plug it in for x and y and see if it satisfies the equation. So you plug it in, the form for x and y. You square it out and collect the like terms. So if you multiply everything out in the numerator, here's what you get. And then you can combine the negative 2t squared with positive 4t squared, and then get positive 2t squared. And you might notice that this is exactly the same thing as the denominator. If you multiply it out, you get the same thing. So this reduces down to 1. So what did we just show? We show that if x and y has this particular form, then it satisfies this equation x squared plus y squared equals to 1. Okay? So that's one direction. So this proves that the point on the specified form is on the unit circle. So let's now go the other direction. So if you have x and y, where x is not equal to -1, but satisfies the x squared plus y squared equals 1, so it satisfies the unit circle equation. What we could do is kind of draw a line between the leftmost point, so -1, 0, and any other point that you're looking at, not the leftmost point, and draw a line through that. So any line that you draw through that looks like this. The reason why it has to have this form, so it's a linear equation, and it has to pass through the point -1, 0. So if you plug in -1 into x, you'll get 0 for y. So it has to be that form. And you'll have some kind of slope t. So we'll call that, that's going to be the t where it satisfies this ugly equation. So let's see how that would happen. So if y is equal to, so if it's on this line, y is equal to t times x plus 1. So what we're going to do is we're going to substitute y in the equation x squared plus y squared equals to 1 to get this equation, x squared plus t squared times x plus 1 squared equals to 1. If you multiply out the x plus 1 squared and then collect like terms for x, this is the equation we get. So we have so if we think of t as a constant here, this is a quadratic equation. If we divide both sides of this equation by 1 plus t squared, we'll get this equation. So maybe it might be a little bit easier to see in the previous form, but note that x equals to -1 is one of the solutions to this equation. So let's look at the previous form, this equation. If you plug in -1, this will satisfy the equation because we'll get -1 minus t squared minus 2t squared plus t squared minus 1. So 1 will cancel out and t squared will also cancel out, and we'll get 0. All right, so x equals to -1 is one solution. And notice how this is a quadratic equation. I don't know if you remember, but very first day of this class, we talked about quadratic equation was equivalent to this form, right? Where P is the product of the two solutions and S is the sum of the two solutions. So we actually know the product, right? The product looks like this. And we also know that one of the solution is -1. So to get the other solution, we just have to flip the sign to get the other solution. So x equals to 1 minus t squared over 1 plus t squared is the other solution to this equation. If you didn't follow that, you could use the quadratic formula as well. You'll get the same thing. So that's the other solution. If you plug this x in into the equation of the line that we had earlier, and then get common denominator and simplify, we'll get y is equal to this as well. And notice x and y, this is the form that we had earlier. So we started with the point on the circle, and we were able to find a t that expresses x and y in this particular way. So we've now shown that you're on the circle except for the leftmost point, if and only if you could write it in this parametric form. There's one more part to the theorem that we haven't discussed yet, is that if t is rational, then the point coordinates on the circle is also rational. So you could we could check this out. So if t is plugged in, if t is a rational number, then 2 times t is a rational number. And t squared is also rational. So 1 plus t squared is also rational. This comes from the fact that rational numbers are closed under multiplication and addition and also division, right? So you create a new rational number by multiplying, dividing, or adding, or squaring. It's still a rational number. And same could be said over here as well. So if t is rational, then x and y, the coordinates of the points on the circle, is also rational. We could also go backwards as well. If you started with x and y being rational coordinates, remember t had the meaning of the slope. So let me go back to the picture here. So you have the slope of the points connecting, so line connecting the -1, 0 and x and y. If x and y are rational, then y divided by x plus 1 is the slope of that line. So that, and again, rational numbers are closed under division and addition by 1. So it's a rational number. So that's it for this video. I will see you soon.